How we doing? Everybody's stronger and more excited about physics every day, right? So last time we spent a lot of time on sort of background pedagogy, context, and a tour through a wide range of materials that can learn. And this all culminated with a particular local learning role that we call coupled learning, and showed you the theory for that. And today we're going to pick up where that left off by actually realizing these things in the lab. So we're going to build electronic versions of autonomous learning metamaterials. All right, so that's where we're going to go today. Then on Friday, we'll do the same thing, but you'll see to a maybe lesser extent with mechanics. All right, so lots of folks have been involved in this work. So last time, Naki was the star. Today, all these folks up here in the top row are going to play a big role. Sam Dillavu, postdoc, Jacob and Ben, they're undergraduates in the lab, Lauren, postdoc in the lab, and also Mark Miskin, who's an assistant professor in the electrical engineering department at Penn. All right, but if I got to single out one person who's really the hero for today, it's Sam. Okay, so Sam is a hero, and so actually I should maybe thank Itai too, because Sam, well, for two reasons. So Sam was an undergraduate in Itai's lab. Okay, so he got to start there. And Mark was a postdoc in Itai's lab. Okay, so Mark, though he's in engineering, he was trained as a physicist. Okay, born and bred physicist, and now in electrical engineering. All right, so let's dig in. So with a recap. So here's the kind of thing we have in mind again. So we've got some kind of physical neural network, could be pipes, could be conductors, and that'll be the case for today. We're going to take some input nodes and output nodes, and we want to think about how to adjust the conductances of those edges so that the outputs are a desired function of the inputs. And with that, we could potentially do a large number of tasks physically, so computational tasks done physically. So this will be a physical neural network, okay, that does these sort of AI-ish tasks. And the cool thing about what we're after is to let the learning emerge from the bottom up by the use of local rules, as opposed to imposing the learning from the top down based on some sort of external rules. Okay, so let me just elaborate on that, just the jargon just a little bit. So bottom up versus top down again. So in the physics world, well, so okay, so what am I saying? So bottom up functionality, that's what we're interested in, bottom up functionality. Well, bottom up or self-assembly of structure is sort of old hat in the soft matter physics world. Of course, nature's been doing this for eons, building complex structures from macromolecules where the ultimate structure that's going to get built, that's going to self-assemble, is sort of encoded somehow in the rules by which those molecules interact. So there's no blueprint, there's no supervisor, top-down telling this molecule goes here, et cetera. It just does it. Learning, the structure emerges from the bottom up. That's what self-assembly is all about. We want the same thing, not with structure, but with functionality. And so far, this is not an engineering thing. This is not a human endeavor yet, okay? But it is something nature has done, but not very often. Brains are the great example of that. So learning emerges from the bottom up in the brain, and perhaps also in the way blood flows through the vascular network. So this fluidic network, the pipes can expand and contract to direct blood flow in different ways, and it does that sort of, we think, with local rules. And my colleague Eleni Catafori is expert in that. Okay, so bottom-up learning of function, very special in nature, and today we're going to do it in the lab using coupled learning. All right, so here's the recap of that. So ordinarily, to program in the desired functionality, you're going to somehow minimize a global loss function that usually involves global operations. We're going to do it with local operations using a contrast function that's the difference in clamped and free powers, which is intrinsically positive. If we do gradient descent on that, we get a local rule. So we're going to adjust the conductance of edge j with time according to the difference in the squares of the voltage drops across that edge under clamped and free conditions. Clamped meaning where we nudge it towards the desired answer. So this is the part of the operation where we show it the answer, where we do the supervised part of the training. All right, so this rule is designed to be implemented in the lab. And there are other local rules that people have designed, and we talked about those, but none of them have been, and some of them probably can't be implemented in the lab. I'm going to show you this one can. That's the first example. All right, so we're going to do it with digipots, okay? Digital variable resistors. And these guys, you can buy them easily. They're cheap. This little package here comes with pins. You can plug it into a breadboard. And this one comes with 128 different resistance values. And inside these things, there's just a bunch of switches and resistors. And if you send a pulse, a little voltage pulse to the proper pin, it'll click it up a notch. If you send a pulse to another pin, it'll click it down a notch. So there's a digital variable resistor, and we're going to work with these, okay? And since resistance is literally our learning degree of freedom, it's our parameter that's going to hopefully self-adjust. Here's the corresponding learning rule. It's a little different from the learning rule for conductance, but basically it's the same thing, just with the there's a sign difference. Okay, it's still based on the square of the difference in clamped and free conditions. All right, so good. So this is what we want to implement, and it's easy to buy these. It's easy to hook them up and connect them into a network with the chosen architecture. But you know, how in the world? Okay, this is a great question. How in the world are you going to implement this couple learning rule without building in a complicated input-output system where you read off the voltage drops, store them, then impose the other bound condition, read off the voltage drops, compute the couple learning, feed it back in, and let it go to town? That's using external memory and external CPU and a bunch of I/O. We don't want that. We want it to be all local. How are we going to do it? Anybody come up with any ideas? Eric is raising a pinky. He has a little idea. It's on a clock. This is going to be on a clock. It's going to be on a clock, right? So with every clock, we're gonna switch back. Every clock cycle, we're gonna compare voltage drops and do this. There's a trick. There's no short-term memory. Our trick is to build twin networks. We're going to build identical twins, and they're going to sit right on top of each other. Okay, one of these twins is going to be dedicated to running the free boundary conditions. One is dedicated to running the clamped boundary conditions, always, and we keep them in the same resistance state. And then we just build some circuitry, and by we, I mean Sam, build some sort of design. Sam designed and built circuitry so that every clock cycle, it'll look at the voltage drop across here. There's like an XOR and a comparator in here, and it'll decide whether we should click these guys up or down one notch. So that's the trick. That's our twin network trick, okay? And then we just will go through the cycle. Every clock cycle will impose the free inputs on both free and clamped versions. They're kept identical. So so we input the inputs and outputs on nodes in this first instance. Well, actually, we always address the nodes. And so here's some wire. Here's the wire, which actually is two. One runs the free, one runs the clamp. Here's the wire coming out again, one from free and one from clamp. And this goes to a different node, and then this splits to different versions of this. Okay, so we hook it up, and so we impose the inputs on the input nodes. On the cycle, we also okay, so this guy did die. We impose the voltages on the output nodes, and we can compare them, do an update, and then just repeat the cycle until it converges. And if it converges, it's learned. Will it converge? Okay, that's the question. All right, so there's Sam again, and there's the circuitry if anybody cares. All I want to point out here is that it doesn't actually implement the full learning rule, okay? It doesn't get this factor of 1 over r squared. In fact, all it does is it clicks it up or down based on which absolute voltage drop is bigger. Okay, so it just looks at the sign of this thing. The sign of this thing. And it clicks it up or clicks it down accordingly. So it's an approximate implementation of the coupled learning. All right, so we'll warm up with the voltage divider, and this is on the homework problem. So here it is. It's two resistors. So think about one of those edges being here and one of these edges being here. And we'll, as an input, apply 5 volts here and 0 volts here. And the goal is for the target to be a desired value in between. Okay. And the solution, there's a multiplicity of solutions. Basically, the ratio of resistances is set by the ratio of desired, the input to desired voltage. It's set by that. So there's a multiplicity of solutions, just like you want in all good machine learning problems. It's over-parameterized. So where it lands up is going to depend on where it starts. Okay. And we'll see what it can do. Now look at this. Here's what it does. So here is a good example. So what we're going to do is train it 1, 2, 3, 4 times to 4 different target values. Okay, so our target values, every 100 steps, will switch from this to this to this to this. And that's this dashed line. So here's the first target, 3.75. Here's the second target. Here's the third target. Here's the fourth target. And then there's 2 curves. One is the clamped voltage. And what we're going to do with the clamping is we're going to take this hyperparameter eta. Remember, this is the nudge factor that goes from the actual to the desired. We're going to set it to be 1/2. So we're going to nudge it halfway towards the desired value. So here's the actual value. Here's the desired value. So it nudges it halfway there. So we're imposing black. Blue evolves on its own, and black is imposed and always kept halfway between the blue and the desired. And the dynamics, it learns quite quickly. Okay? Not necessarily a straight line. Look at this. This is kind of curved in a funny way. Okay? But there it is. And it learns. So the voltage, this very, very simple task, overdetermined, it learned. And one of the cool things about the setup is that we can watch the resistances evolve. And that's the next plot. So here are the resistances. Column A and B, okay? And here they are as in the different shades of gray. And during the learning, and actually, if you look at them, they seem to be going kind of all over the place. But the easier thing to look at is the ratio. Remember, the ratio sets the ratio of resistances sets the actual target voltage, the voltage that comes out here. So here is that ratio. And the answer is this dashed line. So to get 3.75 volts, you need a resistance ratio of about 1/3. That's this light blue dashed line. To get a desired voltage of 2.5, you need a resistance ratio of a little more than 1. Okay? And the resistance ratio evolves to that and stays. Evolves to that and stays. Evolves to that, stays. Evolves to that and stays. Okay? And it stays there when it's learned. So when it's learned, the ratio resistance doesn't change. But look at this. The actual resistance is drifted. Remember, there's the multiplicity of solutions. So it's got a big basin in the learning landscape, and it's just kind of wandering around there. It's because there's a little bit of bias in the circuitry. I don't know. We don't actually know what it is. They're not quite identical. There's a mistake, a slight bias in the way we implement the learning rules. We don't know what it is. But anyway, it causes it to drift. And it's kind of interesting. It drifts almost always so that the resistors tend to go up. And that gives us lower power solutions. And in this case, right, one of them actually hit the rails. Remember, we've only got 128 resistance values. So there's a maximum resistance, there's a minimum resistance. And in this case, up here, it hit the maximum resistance. And right, so when it hits the maximum resistance, it stays. When it hits the maximum resistance, it stays. All right, so there's the voltage divider. So with this, Sam can build his a bunch of edges, and we can go to town. The what? I forget which is so RA is the top resistor, RB is the bottom resistor, and they're kept identical in both the free and the clamped. So we're going to keep the the twins were built as identical twins, and they're kept always in the same resistance states. So we toggle, during when we implement the learning phase, we toggle them up or down in sync. So yes, this is RB in both the free and the clamp. This is RA in both the free and clamp. Yeah. Totally relearned. Yeah, there's no memory in this. Well, the only memory is where you started from. Okay, so where it ends up, or when it first learns, depends on where you started from. Okay, so there's a couple. So the answer is it's the step size and the eta factor. So those two things affect the training. So the step size meaning the delta R that these things have available to them. So that and the nudge parameter affect how fast it goes. Oh, so this is actually pretty slow. So Sam has a little Arduino running this thing. So the global clock is running about a kilohertz. Okay, so it's not too terribly fast. Training step is a millisecond? Yes. Yeah, training step is like a millisecond. And you only can go up or down one click in 1 millisecond.
But I guess compared to our processors and our electronics, this is incredibly slow. But compared to soft matter, this is very fast.
This is right. So and we could make it much faster, obviously. Okay, good questions. All right. So anyway, so Sam designed and built and sort of debugged it with this little thing, and then built a network. And there he is, and there's his first network. Here's our first, something that you would recognize as a network that can autonomously learn tasks. Okay, and there's Sam. This is actually another version I'll tell you about a little later. All right, so there we go. So he built 16 edges, and he strung them together in this funny structure, kind of just strung it up, and it's got 9 nodes. So we have 9 nodes that we are free to use as inputs and outputs. And here's the first thing that Sam trained it to do. It's what Andrew calls allostery. It's a simple one set of voltages in, one set of voltages out task. So here, the inputs are all going to be, the inputs are going to be held at 0, 1, and 5 volts. So those are the 3 red ones. And I don't even know which is which. Okay, 0, 1, and 5 volts. And then the 3 here in purple, we want all to come to 5 volts. So in this case, what you'll notice is the training data and the test data are the same thing. It's just this, the 3 volts. 3 volts, 3 volts, 3 volts. That's training data and the test data. That's what we want it to learn. And like the voltage divider, it just takes some tens of steps until it can learn. And the mean squared error in total, okay, just summing up the mean squared errors for 3 outputs is the black curve, and then the other curves are for the individual values. And they all learn about, well, one learns a little faster than the others, but all about the same time. And then it kind of, fluctuates around. So there's the noise floor. And the reason it's fluctuating is because of this. It's the same thing. So it's learned, but it's drifting around the learned solution. The basin's big. There's an even bigger multiplicity of solutions, and it's sort of exploring that space. Okay, so that's allostery. And more impressive than a voltage divider, but in the end, it's really a fancy voltage divider.
Randomly selecting different outputs, like when you see basically like that they might train quicker or faster depending on which type of
Hold that thought. Hold that thought. It's a good question. I'll show you a plot, a couple slides. But the bigger point behind your question is how do we, is there a smart way to choose the input output nodes? Yeah, and we don't have an answer to that. But all the stuff that Andrew was talking about is sort of designed to get us there. All right, so here's another task that's another level of complexity up. This is a more demanding and more impressive task. If it can do it, then well, it's going to be able to do it. It's linear regression. So we want the outputs to be a desired linear combination of the inputs. So it's a regression task. We're going to try to fit these curves, okay? And the way we do that is by concocting a training data set that consists of 400 input-output pairs that satisfy this relationship. And we use that as our training data, and we flash those data points sort of at random by clamping on the output nodes. And then in the end, we reserve some test data, 20 different values to do the testing, and that's what's shown here, okay, the test data. And sure enough, it can learn. And the two curves here are not for, well, yeah, I forget which is which, but one is for this linear combination, the other is for this linear combination. So you can see it's simultaneously to within the same sort of accuracy learned two more complicated tasks than this. So we're pretty happy about that.
I think that's the order that you feed the input output pairs.
We messed around with that quite a bit, and we didn't see any big change. And probably the answer is because the space of points is still pretty constrained. It's not wildly varying.
Somehow the allostery and voltage divider made sense.
Yeah.
Because you always have the same training and test data. And like the curve, the error just like smoothly went down. That was all good. But now this one, like every step, you're giving it a different signal, and somehow the error is still
So yeah, there's a little bit swept under the rug here. So here a training step means when we flash it, this entire 400. Yeah. So this is after you show it all 400. So we showed all 400, 100 times. This is what in the computer science world they call online training. So under the hood, we could have showed you each resistance is changing every time we flash it a new member of this training data set. But we didn't then tally and test it against the test data until after we did all 400. Yeah, so there's a lot going on here. There's 16 edges. Yeah. Yes.
How does it compare with like the number of like weights you would need in the hidden layers for an artificial neural network?
There's like 4 constraints, and we got 16 degrees of freedom. So it's quite over parameterized, and you would want to do the same thing with an artificial neural network too. But exactly, I'm not an expert in this, exactly how many layers and how big those layers would be, I don't know the answer. I think that computer scientists don't really know the answer either. I think they just try things. Yes, for sure. Absolutely. And Sam has done that. And I'll show you examples of what happens. Again, I got some plots to show you that bear on this question. So you're asking good questions. Yeah, yeah. So this is very typical. All right, let me show you one other task that's even more complicated, more difficult for the system to be able to handle. And it's not MNIST. We can't classify. We don't got enough inputs, outputs to do MNIST with this little baby circuit. Okay, this baby network. But we can classify irises. And this, the image, quote unquote, consists of somebody has measured the petal and sepal width for a bunch of different flowers. So they got 3 species of irises, and they made these 4 measurements on 50 flowers from each species. So that's the data set. And Sam downloaded those. You can get them off the web. And he uses 10 of the flowers from each species for training and 40 from each species for testing. Okay, so that's the data set. I don't know, for historical reasons. For historical reasons. I mean, Sam did a bunch of things, right? In a bunch of different orders. All right. So since we've got 4 measurements, we're going to have at least 4 input nodes. These will be in red, and we'll feed those 4 numbers into 4 output nodes. And also, one of these is going to be fixed to ground, just so it doesn't float all over the place. So we got 1 ground, which you can also think of as an input, and 4 measurements translated into voltages between 0 and 5 volts. So that's that. And then we got 3 species. So there's going to be 3 target nodes. But unlike an artificial neural network, we can't enforce this to be 1 and these zeros for species A, this to be 1 and these zeros for species B. You can't do that with circuits. Circuits don't operate that way. These voltages will always lie somewhere in between the maximum min of the voltages you've applied. So you're never going to drive 1 to 0. 1 could be highest, and Sam has trained it that way, but and that's the way the Naki trained his MNIST network in silico that I told you about last time. So you could look at which one is highest and say that's the species. That works well. Another way that also works is just to look at the mean squared difference between this value and the average of all the other members of the species. So this one, we're going to look at this for species A, this one B, this one C, like before. But now instead of just looking at the absolute value, we're going to compare it to the average of all the species and look at the square of the sum of the squares. So the one which is smallest, the one which has a voltage that's closest to the average of all species in its set will be the species. So that's the way Sam settled on training it for this way. And there we go. Each epoch now we reset what is the average for the species. That's the big blue dots. And then the individual training errors you see progress down in between the epochs and settle down to about a 5% error, okay? Which is close to how, I should have brought a plot. There's only 3 species, so you can make scatter plots of these things. And you can see that you can't, that the data clouds overlap, and you can separate them to like 97% if you draw the best straight line between them in hyperparameter space. So the best thing you can do with the linear classifier, sorry, I got that backwards. 95% is about the best you can do with a linear classifier. If you have a nonlinear classifier, if you draw curved lines through your parameter space to separate the things, you can do a little bit better, 97%. So we're, again, pretty happy with this. So we don't have the image. We just have these numbers. somebody measured the pedal and sepal lengths and widths. And we take those numbers, they're in millimeters, and translate those to voltages between 0 and 5. And we feed that in.
Yeah, so to read out what type of virus it is, you average all the outputs and then you pick the one that's closest to the average.
Yes.
But so then for any input, there's like a whole family of like outputs that would give the same answer, the same correct answer. And if that's the case, how do you pick one of those to be your clamp state?
I'm not sure I understood your question. Sorry.
It's like there's a bunch of like target voltages that, you know, if you just like shift all of the target voltages by constant.
Oh,
you
yeah.
get the same
Right.
answer.
Right. So
But you have to like pick 3 voltages
Yes.
for your clamp states.
that's right. So the first time through, Sam ran through all the training data and he figured out what was the average value of each node for all the 3 species. Okay, and then during the training, he would compare the actual value and he would use those numbers to make the nudges. Right, so that's that. So that was used for the clamping. Okay, so you remember you gotta show it the training. You gotta show it the answer, and that's how we show it the answer. Okay, so to Eric's question, what if we pick different input-output nodes? And here's a big messy plot that shows some of that. So here it is going left to right. Sam did these things in order, 1 through 7. So first classification, then a bunch of allostery tasks with different input-output nodes. Then the 2 same regression tasks, but with different sets of input-output nodes. And you can see it learns in all cases, and you know the resistances. Some of them, well, he plotted some of the resistances, and they drift around, and some hit the rails again. So we can't really see any big difference between how we choose the input-output nodes, and there's not too much memory that we can figure out. There's not much we can see about going left to right. But basically, you know, it doesn't, you know, if you then go do another allostery task, it basically has to start from scratch. Basically, when it hits the rail, you've lost a learning parameter. Yeah, so it becomes less over parameterized, but it's still got enough degrees of freedom that can do the job. Yeah, it depends on what your application is. If you're interested in saving power, sure. Actually, literally actively try to build in some bias so that it learns it. It's got lots of learning parameters, but there's a little bit of bias. So after it learns, it kind of drifts up to having the highest resistance state on average you can have for all the resistors. Then you minimize power. So it could be a good thing. On the other hand, if it drifted too fast, it would certainly harm the learning. Yeah. Yeah. Yeah, there's 16 edges and 9 nodes. Yeah, it's literally this picture here. Yeah.
It's not a toy diagram.
No, it's literally it. Yeah.
You know, like, would you expect to see something like catastrophic forgetting if you had a bigger network where it like remembers a bunch of tasks and then suddenly forgets them all?
So with these, as soon as we if you train for task A and then train for task B, it forgets task A already. So it immediately forgets it. Yeah. So to have memory, you're going to have to build in some nonlinearities to this. So this is a really cool question. It's something that we're thinking about and following up on. But nothing to say now.
Confused about the classification as the allostery regression. You had your inputs, they were whatever they were, and the outputs, whatever. And that was fine, there was no problem, but then you got the classification for some reason which I'm not catching. You couldn't just clamp the outputs to whatever you wanted them to be for.
No, we do. We do that also. We do that also. What we want them to be is the average value of all the species.
So then
Or-
if there's outputs, so it's like it's 1, 0, 0, 0, 1, 0, 0, 1.
We're clamping all three outputs. So in species A, we want output node A to be the average value if we show the circuit all the different members of that species from the training data set. And then the other two will also fluctuate around as we feed it in that training data for species A. Output nodes B and C will also be changing. And we clamp those also to the average value of when it's A.
So it's 1, 0, 0, 0, 1, 0.
Yeah, you can't do that. You can't do that.
That's what you did before.
No, not what we did before. You can't clamp it to 0. It can never reach 0. It'll never be 0. It'll be somewhere in between 0 and the maximum voltage we input. Yeah. So yeah, sorry. This is we also trained it like Naki did, where you want it, where you decide the species based on the max, but based on which node was the biggest. And that worked, but it wasn't as robust as this method.
It's 0 because your resistor doesn't go to 0.
You,
You can't, because you have a ground there.
you got a ground. No. Yeah. For the allosteric case? Yeah, for the allosteric case, yeah. So in there, right? In this one, there's 2 inputs and 1 output. In this, there's 2 inputs and 2 outputs. In this, there's 3 inputs, 3 outputs. This, there's 2 inputs and 4 outputs. So we did all kinds of different allostery tasks. No, you don't have to. Yeah. So you've got that network and you've got 9 nodes and the world is your oyster. You can choose those nodes to do anything you want. You can choose them to be inputs and outputs, any number, as long as you got less than 9 total. You can see in this case, right? I mean, there's only like 3 free nodes in the end. So we almost maxed out the circuit. There's still more learning parameters than there are constraints, but we almost maxed out the nodes. All right, so let's now do some variations of this with the same circuitry. And I tried to motivate last time that we're looking for brain-like advantages of this. You know, this autonomous learning system should get some brain-like advantages, but there's some ways which our circuitry is plainly not very brain-like. And one is our brain doesn't work on a clock, right? So you could say, well, you know, Durian, this is you've imposed global information with a clock. Okay, that's not very local, is it? There's an external overseer, you know, whipping the circuit every, you know, so-and-so. So can we get away from the tyranny of the clock? And the answer is yes. So this is where Jacob Wyckoff, undergraduate in the lab, he's now graduated, came into play. And he built a little modification to these edges, okay, to Sam's design, where we could twiddle a parameter and choose the fraction of edges that get updated every cycle. So C is going to be the fraction of edges that get updated each clock cycle. And you can see now that this is on a clock because there's a time scale which the lights are flashing. And the LED that's on shows you the edge that's being updated. So every clock cycle, in this case, there's, I don't know, maybe a third of them being updated. And Jacob can vary this fraction of edges from 0 to 1. Okay. Well, so 5% to 100% in this case. And look at this, 5%, it can still learn. 100%, well, you saw it learn before. So this is for an allostery task. Okay. and it can learn. So the clock doesn't really play a big role if you're only updating 5% at a time. If you look at this carefully, you might notice something interesting. Everybody notice anything interesting in this plot? What's the level of noise? Level of noise is different for these three data sets, isn't it? The level of noise actually goes down if you update a smaller and smaller fraction. So the biggest noise is for when you update them all simultaneously. If you update them a little bit at a time, you actually learn better. We get better solutions. Funny enough, we update a small fraction. And this harkens back to something called stochastic gradient descent, which is a trick for avoiding minima in artificial neural networks, where you sort of update only a fraction of your neurons at a time. And Naki's got some arguments actually for maybe literally mapping this onto stochastic gradient descent. So anyway, that's cool. So the clock doesn't matter too much. Here's another thing that's different about our circuits in the brains. Our circuits relax really fast. So remember, we're changing on a clock, and as soon as we change the resistance, bam, the circuitry, the physical degrees of freedom relax to their values. There's an RC time. We didn't build in any, there's no capacitors in the circuitry, but there's stray capacitances in your circuitry. That's always the case. So there is an RC time for the circuitry to relax, but basically it's relaxing very fast. The physical degrees of freedom are essentially always equilibrated when we learn. But that's not true in the brain. In the brain, it's slow and noisy. The action potentials propagate over, across the neurons at a slow speed, and the brain is evolving over those same sorts of timescales. So your brain is learning out of equilibrium. So what about this? And might there not be advantages to learning faster, right? I mean, can't we flash data faster and, really push it hard to learn faster and faster? Well, we can't actually make the flashing the data faster or updating the resistance faster, but we can make the equilibration slower by literally adding capacitors across all the edges. So Sam did that. Okay, here's a big honking capacitor that he plopped across those resistors, and that slows down the relaxation of the physical degrees of freedom of the circuitry, so that you can learn on a time scale that's fast or slow compared to equilibration. You can try to adjust the resistances before the currents have relaxed. So you're working with faulty data, literally. And does it learn? Seems like it wouldn't, but actually it does. So Naki simulated it and Sam built it. Here's the trained mean squared error as a function of the learning rate compared to the equilibration rate. So if we're much less than 1, you're in the quasi-static regime. Slow learning, the physical degrees of freedom are always equilibrated. Far to the right, you're learning fast and the physical degrees of freedom have not relaxed while you're still trying to update the resistances and probably shouldn't learn. But look at this, it does. It still learns. Not quite as well. And the difference is more dramatic in Naki's case because there's no noise. We've got a noise floor, and it goes up from the noise floor a little bit. His noise floor is set by just numerical precision. So this in principle is 0. Okay, but then it jumps up to some value. Okay, so this is kind of cool. It says that our learning speed is not limited by the physical relaxation time of the circuitry, and that's a nice brain-like thing. Another variation, power optimization. We can literally build in, and I mentioned this last time, here's a variation of the coupled learning rule where we're going to throw in a little bit of free power. So it's going to minimize this whole thing in square brackets, which is a combination of the error and the ultimate energy cost of running the circuitry. And depending on how big you make epsilon, this is more or less important. If it's 0, then it's going to be perfect couple learning. If it's 1, then actually the threes cancel and you basically are left with directed aging. And the cool thing, well, I mean, it should work and it does work, is you crank up epsilon, then then there's a trade-off between how well you learn and how much power the circuit takes to run. So here it is plotted parametrically, the error versus the power. So when there's high power, that's when epsilon is 0, and this is when so epsilon's going from 0 close to 1 up here, and there's the trade-off in both experiment and in simulation. So that's a cool thing. And this is what you might call regularization. It's imposing a little bit of bias on your learning to do an extra thing that you think is good. So that's fun. And then finally, how robust are these things? This is another important issue. Our brains are famously robust compared to computers, right? You can't damage your computer very much at all physically before it totally dies. But that's not true of our brains. You can remove half a brain and it works at quite a large extent. So what about our circuitry? And this is what Sam did. He systematically damaged the circuit by just removing edges one at a time. So he snipped them. And every time you snip it, you may or may not have to relearn. But if you have to relearn, you can still learn well. So the noise floor doesn't change. We've removed learning degrees of freedom, but we get the same noise floor. And actually, this plot is not representative of what happens. More often than not, you remove an edge and you don't have to retrain much at all. Okay, this is more the norm. This little spike, small spikes are the norm. Large spikes you have to hunt. These are the so-called important edges, which are rather rare if you harken back to Andrea's lecture. There's only a few edges that are important. If you snip those, yeah, you got to retrain. But most edges are not important. If you snip those, you don't have to retrain. These two are just a little bit important, log scale. You know, the jump in error is not much at all compared to the biggest cases. All right, so this is brain-like, and that's cool. And for us, this also signals something very, very important. It says that if we build something that's damaged out of the box, if there are manufacturing errors, our system doesn't care. It's just going to learn around them. And let me tell you a fun story. Okay, experimentalists, right? You build something, and if there's a mistake in your apparatus, it doesn't work, right? That's what happens. That's not what happened to Sam. He built his circuitry, and it just worked. The thing wanted to learn, it learned. But then he would switch around which nodes he's using or inputs and outputs, and suddenly it didn't learn. And he discovered only after the fact that's because there was a particular edge that became important for that set of node selections, and therefore it couldn't learn. Okay, so these things are really robust. You can build them with mistakes, and it doesn't care. Contrast that with our usual experience as experimentalists, and contrast that even more with what happens in the field of neuromorphic computing, where you want to build special chips to do these AI things in hardware, and they have to build in tons and tons and tons of backup stuff to guard against and prevent against and mitigate manufacturing errors. We don't have to at all. It's like the brain. Who cares how your brain hooks itself up, okay? All the neurons are different in some little ways. It's still going to learn. Same thing is true with our circuitry. So this is cool. And it says that we are going to be able to manufacture these, and we're going to be able to scale them up, and we're taking some steps to do that that I want to start to tell you about now. We've got a question first. Good. We're allowed to make them smaller. We can, and we are. And this is our first step right here in doing that. Okay, so we've been talking with Mark, and Mark came up with this idea for how to use resistors as transistors as variable resistors. Okay, so Mark designed some circuitry that I'll show you about next. But basically, the idea is we're going to have two transistors as our learning degrees of freedom, and we're going to tie a capacitor across them and store a charge on that capacitor. That capacitor charge will set the gate voltage, and the gate voltage will control how easy it is for current to flow through the transistor. So it's a three-element thing, and basically the gate voltage is the learning degree of freedom, and they're identical transistors. They're held at identical voltages, so they're kept in the same states. So that's the twin network trick. So we're going to implement the twin network trick, not with digipots, but with transistors as the learning degrees of freedom. And as I said, that's Mark's design. Actually, Sam designed it also. And here's an example of the network he built. And there's what the circuitry looks like. Cool thing about Mark's idea is actually, well, it's just a bunch of op amps and a multiplier. And the idea is to combine some voltages in such a way that you can literally compute the, you can run a current, the output, you can run this current to the gate voltage, to the gate capacitor. So, this will put out the error signal in proportion to this. So this current will adjust the gate voltage if you're not trained. So there's no clock. It just is always evolving as long as we dump the current to the capacitor as opposed to ground. So we can lock and we can learn. Okay, so during the learning phase, we'll have the switch here. During the testing phase and the operation phase, we'll lock it here. Okay, and there it is up close. So Sam and actually Ben Beyer helped build these things. And Sam gets compliments and insults when people look at this and say, okay, this is the biggest breadboarded circuitry I've ever seen. And Sam says, feels good. They said, oh, geez, what am I doing? So the reason why you want to breadboard it is because you want to test it. But if you can make it on breadboards with transistors, you can also micro-manufacture it. And that's the idea. Okay, so does it work? Okay, well, let me tell you something cool about this system as opposed to the digipod system, is that this is intrinsically nonlinear, but in a weird way. So here are the IV characteristics of the capacitors. So the effective conductance depends on the average voltage of the source and drain, the two ends, as well as the gate voltage. So for different gate voltages, here's the conductance. And look at this one. This conductance doesn't depend on the voltage conditions that the transistor finds itself under. Okay, but it does if the gate voltage is low. So this is a source of nonlinearity. These are not ohmic things, okay? But it's not like, V equals, I squared something. That would be a funky nonlinearity, okay? That might be simpler to think about. This is a different kind of IV characteristic, which is also nonlinear. And with nonlinearity, we hope will come more functionality. One of the secret sauces for AI is to have nonlinearities. And why is that? Because there are some tasks that are intrinsically nonlinear. Famously, the XOR function is not a linear combination of the inputs, right? The idea of the XOR function is you want to tell, are the inputs the same or different? Okay, so there's the truth table for XOR. It's 1 if the inputs are different, it's 0 if the outputs are the same. So you cannot compute the output as a linear combination of the inputs. Or as a classification problem, by contrast with the OR function, which is linear, here we can draw a line through this truth table to separate the two classes, the green and red. Here, if you cannot draw a line that will separate greens from reds, right? So it's hard because it's not a linear combination of the output. The output's not a linear combination of the inputs. And you can't, as a classification problem, you can't simply draw a line to do this. no matter how big we made the Digipod version, you could not train it to do XOR. You think greater capability comes with larger networks, that's true in general, but not if the network is linear. Yeah, if it's linear, the circuitry boils down to like a fully connected well, having all the inputs connected to all the outputs. It boils down to that. All right, so little I almost said excite on SOAR, but I meant to say aside on XOR. So this was famously shown that a simple neural network cannot compute the XOR function. Okay, and when Marvin Minsky and Papert proved this, people got really depressed. And this is the first of a large number of depressing results in the nascent field of AI, which people sort of, there was like an AI winter for like 30 years, and the XOR function was at the beginning of this. So this is the first of a string of failures and difficulties and roadblocks that people eventually had to overcome. And the solution to it is nonlinearity and depth. Okay, so the trick is to add depth. You got to add this hidden layer, and you've got to make a nonlinearity in the way you add up the weights. So, for example, a tanh function or something. What people nowadays use is the ReLU function. I forget what that means, but basically you truncate it if it's negative and you keep it if it's positive. Or you can do a tanh function or something like that. So this is the smallest network that you can use to compute XOR, smallest artificial neural network. It's got 1, 2, 3, 4, 5, 6 learning parameters, and it's got nonlinearities. It doesn't learn very easily by gradient descent because it's not terribly over-parameterized. This tends to get stuck. And the way you get around that is by adding more hidden layers or more nodes, okay? But get some more depth somehow. Further side, yeah, that over-parameterization is really important in general. And we got the same sort of issues. And there's a really cool thing that I will not talk about, but it'd be cool if you want to learn about, called double descent. And the idea here is it's kind of counterintuitive if you think about it. In the AI world, you always have more parameters and constraints. So don't you end up just overfitting the data? You end up fitting all the little wiggles, so that when you show a new training data, when you show it test data, it makes wildly wrong predictions. You've overfit it. So you put in some regularization to get around that, avoid that overfitting. So it turns out that yes, with over-parameterization and regularization, you can do really, really well. There's some really cool mathematics that's totally unintuitive behind that underlies a lot of AI, and the same sort of stuff is going on. And Jason Rocks, who is Andrew's grad student, is working with Pankaj Mehta, who's a biophysicist and AI guy at BU, who's super expert in applying big data and AI type things to biological situations. And they've got some interesting ways to actually model this analytically. So I can really recommend this paper for this. Anyway, that's enough asides. And let's see if we can do it. So here is Sam's network. So he built 32 of those edges. He and Ben built 32 edges, and they strung it up to be 16 nodes. And to do XOR, here's the way that, well, he also imposed periodic boundary conditions. So how many experimentalists have ever implemented periodic boundary conditions? We did it. I guess that's fun. Anyway, we don't have to, but we did. And so here's the way that he ended up programming it to do XOR. So we're going to impose a couple fixed voltages, kind of like we did before, right? We would ground some nodes. So here, instead of grounding it, he made this one be 0.1 volts and this be 0.3 volts. Then he imposed our input data through these two nodes, and he read the output. We want an output. We're going to do this so that if we get sort of one class, we want a negative number, one class, we want a positive kind of number. or we want one to be 0 and one output to be large. Actually, that's what he's going to do. And to do that, we're going to look at the difference in voltages between these two nodes. So the output signal we're going to train on is the difference between these voltages, difference between these nodes, as opposed to the node values themselves. All right, and look at this. It can learn. So here's the truth table evolving with time. So it starts out, basically all the voltages are low and evolves towards a large voltage difference between the two output nodes in the case that you want to have a 1 where the inputs are different, and it has difference in output nodes close to 0 where the inputs are the same. So it managed to learn. And this plot actually, you can kind of see through this plot which nodes are important in a different way from the way Andrew was talking about importance. Clearly, the nodes that are acting non-linearly are going to be important for this. And those are the ones that have low conductance. And the low conductance ones are the ones with narrow pipes. So the pipe widths are changing as we learn. Okay, and they're colored here. Sam just colored them. He went nuts on this plot according to how fast they're changing. But basically, the ones which have thin pipes are going to be super important for imposing the nonlinearity. So that's cool. That worked. XOR can be learned. Another cool thing about this is, of course, we can watch it learn and look how it learned. It learned in a very particular way. The first thing it learned was to get the average output. The second thing it learned was to minimize this pattern. And the third thing it learned was to minimize this pattern. So you can decompose it into modes, and it learned in order of mode complexity. It did the simplest one first. It did the more complicated one second. It did the most complicated ones last. That's this green right there. So it learned in order of complexity. And this is something also people can see in AI type situations. That's cool. Here's some more tests we can do. We can do nonlinear regression. So here we're going to try to fit the open circles. So here's the input, and the training data are these circles, and the output, the test data, the test results are these curves here. And look at this. It also trained in order of complexity. So first, it shifted this line. Here's the initial line. First, it shifted the value. It just moved the line over. Then it changed its slope, and then it curved it. And indeed, if you can decompose it first into the mean, then slope, then curvature. Yep, trained in order. And it can fit this nonlinear function. Not perfectly, but pretty darn well. We gave it a hard task, right? That's a pretty drastic nonlinearity to try to fit, and did a pretty good job. Here's a movie of another nonlinear task. So we're going to learn classification. What have we got here? We've got two inputs, and the training data are the blues and the blue and the gold data points. So if your input outputs lie in this region of the plane, they're blue. If they're in this region of the plane, they're gold, right? So you could draw a curve that separates them. So this is a nonlinear classification task. And at time 0, the network's not trained. Here's the line it's trying to draw. It thinks everything above this black smear is blue, but it's wrong. It thinks everything below the black smear is gold. Well, that's right. Okay, but clearly this is wrong. So somehow we got to evolve towards this. And here, watch it learn. And if you watch carefully, I can play it a couple times. It's going to learn in mode order again. Basically, at time 0, the decision boundary was straight, and then it just rotated it, and then it curved it. The last thing it does is curve it. There we go. All right. And there's more nonlinear classification tasks, including training XOR. Okay, so there's training XOR. Look at this. There's 2 decision boundaries, right? Can't draw one line, separate them. You have to draw 2. And it manages to do that. All right, so we're pretty happy with that circuitry. It's doing its job. So we're encouraged now with our successes in breadboarding to take steps towards micro-manufacturing this. And the first step to do that will be to scale it up to networks of hundreds of edges. And Sam is not going to breadboard those, but we're going to do it on printed circuit boards. And postdoc Lauren Ullman and Mark's student Harunya Sivakumar have been leading the charge on that. So Lauren has now got a bunch of these we're testing, and it's looking good. So we're excited about that. And if this all works, we think that we can manufacture an order of 10 million of these guys on a reasonable size chip. Okay, so those are our dreams. Okay, it's massively scalable, right? There's going to be, if you manufacture it, there's going to be mistakes galore. Okay, and we don't care. It's still going to work. It's robust against those manufacturing errors. Okay, so you know, if you get all these chips acting in parallel with lots of, you know, we think we can do lots of good stuff, and you know, I actually, yeah, we've got a design in mind for a 3rd generation. I didn't tell you about that, and we can put actually 100 times more edges per chip than the previous design. Okay, so we're starting to get close to the number of parameters that exist in large language models. Wouldn't that be cool? If it worked, well, here, question first.
Is this an all-to-all network being printed on the chip, or only those?
Yes, so there's a good question. So we haven't designed it yet. We haven't laid it out, right? We have not taken those steps. But what our plan is to do either a crossbar array or to do a square or triangular grid, right? So those are things to be determined, and that's actually why we want to build the printed circuit board version with hundreds of edges, so we can test some of those network geometry architecture questions, which we can't do with the breadboards. They're too fragile, and we don't have enough of them. So that's why we're taking these sort of baby steps. Can't just jump right to the micro manufacturing, unfortunately. But if we can get there, right? If we can really do this, we're gonna have some advantages. Like I told you earlier, analog computing has an advantage in terms of energy and speed. And here it is. Here are some estimates we have. So with our approach, 10 to the minus 18 joules per parameter. Compare that with the most efficient chips on the market today. We're doing 1 million times better. Okay, so if this would disrupt AI, if we could do AI with these kinds of learning chips, you won't have to build a power plant next to each data center. Wouldn't that be nice, right? So that would be great. We're super, super excited about that. Of course, we don't know if we'll get there. When you scale things up, other things are going to happen. We have no idea how far this can be pushed. Yeah, there's lots of questions about architecture, about noise, about lots of stuff. So we'll see where it can go, but for sure, we're going to have at least niche applications with thousands or tens of thousands or hundreds of thousands of edges, maybe even millions of edges, if not, 10 to the 12, that will do things like you could build them into sensors, like a camera, and do AI things right there in situ, right? This is called edge computing. You could do edge computing and adjust it in the field. And actually, that's one reason why Mark is interested in this, because he would like his robots. They got a power problem, right? And you want to make them smart. You want to talk. Think of them as a network. They're going to interact with each other according to some rules that can be learned, but without using a lot of power. And also to be able to adapt on the fly. Wouldn't that be cool? So there's a lot of good stuff in sight for this. And so that's it for electronics. Next time we're going to move towards mechanics. And I'm going to skip fluidics. We could do fluidic networks, but hey, we've basically done them because there's an analogy between electrical circuits and fluidic circuits. They're basically the same, except for voltage pressure mapping. Okay, so if you can do it for electronics, you can do it for fluidics. And you can even build in nonlinearities, like using check valves as opposed to diodes. They're basically one-way components, like current flow in one direction. So there are things there that we're working on, but I won't tell you about. Nothing published yet. Interesting report. But I will say that mechanics is harder than electronics, which is a little bit ironic. Because of course, electronics is a much newer technology than, building bridges and things, right? So, but it's true. And one of the reasons why is because force is a vector, whereas all these other things involved in the fluidic and electronic circuits are scalars. So it's a more complicated problem, just intrinsically. So it's harder to simulate. And if you're going to build it in the lab, as I'll show you, you also have to integrate electronics with the mechanics. So that presents some challenges. But I like this. I'm excited about it. And one reason for me is it harkens back to my long-standing work in jamming and particulate systems. So, pack together a bunch of grains or bubbles and you get these nice networks of contacts and force chains and whatnot. Okay, so it harkens back to that. And I was talking to Vidyesh, and he's actually trying to train mechanical networks to do interesting things. Okay, so it's going to be a cool area of research to do learning in mechanical networks, and to think about analogies of say even biological versions like biofilamentous networks. And can you think of those as learning systems in some way? Okay, so Andrew's working on that with John Crocker. So I'm excited about this. And let me leave you with a movie. Okay, so here is actually an active mechanical system for my lab. And this is work by my PhD student, Anthony Kecko, who's since graduated. And so this is a fun mechanical system, which is doing some kind of funny flow towards the center, sort of converging towards the center. And I'll just leave that there, and I'll offer 10 points, 10 very, very, very valuable points to anybody that can figure out what this is. All right, so that's it for today. Thank you. Be glad to try to answer more questions. I guess if it breaks, you don't want fluid squirting all over the place. So, so maybe not as robust. Who knows, right? Electrons tend not to leak out of broken wires. So the way it fails will be different. But in terms of the learning capacity, if like whatever mechanism you will build on an edge to adjust its conductance, like maybe you've got something that will squish down the pipe in the center. If that mechanism doesn't work, you don't care, right? If there's if some fraction don't work, you don't care. It should have the same properties. Okay.
Given that your networks are kind of restricted to having spatial couplings, kind of reminds me of like a convolutional neural network, right? Solving the thought about your problem.
So what can I say about that? if you put these on a chip, then there's going to be some constraints about how you can connect things up because there's only so many layers you can have. So your circuitry, the architecture of your circuit is going to be a little bit limited. In the lab, we're not limited at all. We can wire them up any way we want. We can have long range connections. And we kind of think it doesn't matter too much, the fact that we're not limited by this on chips, because the system is intrinsically recurrent, right? If you apply a voltage here, it affects the currents everywhere. Maybe not to the same degree everywhere, but it can affect it everywhere. So we think that that's not going to be a limitation, but we don't know. That's one of the open research questions. In terms of making a convolutional neural network, I don't know about that.
Big jump from listener networks to networks. There were a couple of different points that escaped me. One thing which you didn't mention, which was questions like learning rules or feedback. Andrea mentioned that for non-linear.
Yes. So let me show you that. Where is it? There it is. So we use the same local learning rule, but implemented as exactly as we think we can, right? So this is literally the exact local couple learning rule that we calculated. And we run a current in proportion to this. So the gate voltage is updating according to this. This implements this pretty exactly, okay? And the question of how important that is for nonlinear situations, I don't know the answer to that. This one, I can say it doesn't learn as easily as the linear case. It takes it longer to figure out how to take advantage of the nonlinearity. And I don't know whether that's because it's just intrinsically harder or because of the nonlinearity is weird, or if it's because of a mistake in the learning rule vis-a-vis what Andrea talked about. So it's an interesting question.
Diagram. About this. I understood the inputs and outputs, but now there's this timelines.
Think about those as being just like a ground. So they're just fixed voltages. Why do we need two? We couldn't do it just by grounding it. It didn't work. It didn't work. So we wanted to raise the voltage conditions so that the, so think about making this, if you want these guys, all the nodes to be somewhere between 0 and 5, make this one be 0, make this one be 5. And no matter what you do with the inputs, it'll do that, right? So if, for example, doing XOR, you might want to ground both of the inputs. But if you ground these, and these are grounded, then the whole circuit is dead. So you got to have a high voltage somewhere in the system. Yeah, so funny experimental things to worry about that you wouldn't have to worry about with an artificial neural network. Hey. The periodic boundary conditions, just literally, there's literally an edge right here, and then a wire that connects over to there. Why do we do that? It was a way of using this edge. So if we didn't have the periodic boundary conditions, this edge wouldn't do much. We thought it was a way of making all the nodes sort of see all the edges a little more even-handedly.
So did you try open boundary conditions?
Oh, we did.
Is it different?
Oh, yeah. It didn't learn as quickly.
With it? Do you think it's just reduction in number of parameters?
Oh. Yeah, I don't know. I don't know. All right, good. Thanks, folks.